Hi. Now in this example we're given a sequence of positive integers is defined by the first term u1 equaling 1 and then the n plus 1th term un plus 1 equals the nth term un plus n times 3n plus 1 where n is any positive integer. And what we've got to do is prove by induction that un equals n squared multiplied by n minus 1 plus 1, again for any positive integer. So if you'd like to have a go at this, if you haven't done so already, just give you a moment to pause the video, and as usual do come back and you can check your work solution with mine. Okay, welcome back. If you had a go, let's see how we do this. So first of all, the usual way, what we have to do is prove that it's true for when n equals 1. So we'll just say when n equals 1, and we look at the first term. Okay, we're using this formula here. So the first term, u1, would be equal to 1 squared, okay, multiplied by 1 take away 1, which is going to be 0, plus 1. And this turns out then to be 1. And we were told that u1 equaled 1. So you can see that this works when n equals 1. So we'll just put therefore true when n equals 1. And what we now have to go on to do is assume that our statement is true for some particular integer value for n. So we assume true for n equals, say, k. K is a positive integer. And so therefore what we're saying is that this statement is going to be true for n equals k. So you're going to have uk is going to equal k squared multiplied by k minus 1 plus 1. Now what we need to do is show that this statement is going to be true when n equals k plus 1. So what I'm hoping to work towards is that uk plus 1 is going to equal k plus 1 all squared multiplied by k plus 1 minus 1, in other words just k there, and then plus 1. And to do that, I know this statement is always, well, it's defined, so we can work with this statement. So we know that uk, we'll just put here, so uk plus 1 is going to equal uk plus, then n is k here, so that's k times 3k plus 1, k times 3k plus 1. Now we've got uk, we're assuming it's true for this value, okay, so we got that there, so we can substitute that in as k squared, k minus 1 plus 1, and then we've got plus k and 3k plus 1. Now if I expand this, okay, we've got k cubed minus k squared and then plus 1, and then expanding the last bracket gives us 3k squared plus k. And now if I just put the plus 1 on the end, so I'm starting to head towards this format here, what we've got is k cubed, and then if I group up the k squared terms, we've got plus 2k squared and then plus the k there, and then close that bracket off, plus 1. So I've got to now work with this. I'm trying to get this to now come to k plus 1 all squared here, and then in here k plus 1 minus 1, in other words k. So that's giving me some kind of guidance to where I want to take this. So we'll just put therefore uk plus 1, carry on down here. uk plus 1, well, looking at this, what I can do is pull out k as a common factor. So if we do that, we've got k there, and we're going to be left with k squared plus 2k plus 1 and then plus the 1 on the end. And what we've got here is a quadratic expression which factorizes. It's going to be k plus 1 all squared. And then we've got the plus 1 here. Now if I just turn this round, swap it round, we've got k plus 1 all squared, and then for k, if I write that as k plus 1 and then subtract 1 and then we put the plus 1 on the end, I've now got the form that I was expecting. Okay, we've got k plus 1 all squared, and here we've just got k plus 1 minus 1 and then plus 1. So hopefully now we can see that it is true for n equals k plus 1 on the basis that it is true for n equals k. So we'll just write that in here, that therefore if true for n equals k, then true for n equals k plus 1. And on that basis we know that it's been proved true for n equals 1. Okay, we did that at the beginning here. So since it's true for n equals 1, then it must be true for the next integer up, n equals 2. And if true for n equals 2, must be true for n equals 3 and 4 and so on. So therefore it's got to be true for all positive integers n. So true for all n being a member of the positive set of integers. Alright?